Hi, everybody. Welcome to our discussion with Chapter 6, where we're looking at quantities in chemical reactions. So this chapter really ties in everything that we've been looking at since Chapter 1, really. This is the culmination of what we've been working with. And we talked a little bit about this idea of quantities in looking at stoichiometry in Chapter 5. And so we're going to take especially the information that we learned in chapters 3, 4, and 5 and really applying them here, but you will see pieces from 1 and 2 as well. So you're going to be writing chemical formulas, you're going to be balancing chemical equations, and then we're going to be doing dimensional analysis. So remember, dimensional analysis or converting units is what we looked at in chapter 1, and we're going to be using that again here. So we have our learning outcomes. Again, the main purpose or the main idea of this chapter is this idea of stoichiometry that we discussed in chapter 5. Again, just meaning that we want to relate the amounts of reactant and product that we have for any given reaction. So you will need a calculator for this chapter. It's pretty math heavy. Make sure you have some scratch paper and make sure you have out a periodic table because you will need that. We're going to be doing lots of calculations with it. But the first thing that we really need to understand in this chapter is the idea of the mole. So what the heck is the mole? That's the question, right? What is that? And in chemistry, pretty much what this means is it's another way for us to describe an amount of objects. So a mole is just an amount, and that's it. It's the same way that in baking, we usually talk about the idea of having a dozen of something. You can have a dozen cookies, a dozen muffins. Well, you can also have a dozen of anything outside of baking, right? We can have a dozen water bottles, we can have a dozen pencils. It's the same thing here with a mole, where 1 dozen equals 12 of any object. 1 mole equals this huge number right here of that object, 6.022 times 10 to the 23rd. So this number is going to be very important for us. It is a constant, so it will be given to you on your exam, but we're going to be using it fairly a lot, so you'll probably just get used to remembering that number. But you can see down at the bottom here, I wrote out our conversion factor, so, or rather an equivalence statement, so that we can go back and forth between a mole and an amount. And so 1 mole is always going to equal 6.022 times 10 to the 23rd. And for us, most of the time, our units are going to be atoms or molecules, but just like a dozen, it doesn't only have to pertain to chemistry. You can use Avogadro's number for anything. And so a lot of the time, we'll use the terminology formula units so that we're saying, all right, we have this amount of something. It could be atoms, it could be molecules, it could be something else. We just say formula units to say it is something. So just be aware that you could see any of those units, atoms, molecules, or formula units. And one way that we can describe Avogadro's number in a more simplistic manner is using this idea of just calling it Na for the number of Avogadro. And that way we don't have to worry about writing out that huge number all the time. Now, why is this number so giant? It's 10 to the 23rd. And remember, that means that this number is greater than 1 because its exponent is positive. So this number means we're moving this decimal over 23 places. That's a huge number. And when you think about it, it makes sense because atoms are so tiny that we need a lot of them in order for us to actually witness some kind of chemical reaction occurring. So rather than talking about 10 to the 23rd atoms and using scientific notation for everything, we use the mole to make things a little bit more simplistic. But again, this is about the amount of objects that we have, and that's it. So a mole can be a different weight for varying objects. I can have a mole of bricks or a mole of feathers. Both of those piles will contain 6.022 times 10 to the 23rd of that object. But a pile of bricks and a pile of feathers are going to have vastly different masses. So I do want to just point that out before we start to see the mole in a little bit more light. So let's look at a conversion between these. So if we are told that we have a certain amount of moles and we want to find out how many atoms that is, well, we know that there is a relationship between moles and atoms. We just looked at it, right? So again, here's our equivalence statement saying that 1 mole is equal to Avogadro's number. And then here we have our 2 possible conversion factors. So remember, in order to get to a conversion factor, all we're doing is taking the information from our equivalence statement and making a fraction out of it. So how do we determine which one of these 2 possible conversion factors we need to use? Remember, you always want to start off a dimensional analysis problem with whatever value is given to you in the question. In this case, the value given to us is 0.732 moles, so that's what we're going to start with, which you can see down here in red. Since we have moles in our given amount, and we want to get rid of moles, that means that moles has to be on the bottom of our conversion factor. So that's how we know that we needed to use the conversion factor on the right. And again, I just abbreviated it as NA. Remember, NA is 6.022 times 10 to the 23rd. So if you go into your calculator, you should be able to type in 0.732, multiply that by 6.022 times 10 to the 23rd. So again, make sure that you're plugging in scientific notation correctly. And when you hit enter, I end up getting 4.41 times 10 to the 23rd. Make sure you try this out yourself, feel comfortable with your calculator, and make sure you're understanding which buttons you should be pressing. Now, if you had this kind of question on an exam or a homework, I do want to point out something. You should always have 3 parts to your answer for any kind of stoichiometry problem. You should have the quantity or the value. In this case, it's 4.41 times 10 to the 23rd. You should have the substance in question. In this case, it's aluminum. And then, of course, like any other problem we do, you need to have the units. So in this case, it would be atoms. And I would mark correct if you wrote formula units instead of atoms. That's fine with me. So even though in this particular example, we went from moles to atoms, we can just as easily go from atoms to moles. We would just divide by Avogadro's number instead there. So let's look at a case a little bit more specific where we can use this idea of a mole to atom conversion, but with chemical compounds. So we have something called the intermolar ratio, and I'm often going to abbreviate this as IMR. And I apologize, my stylus isn't working as well as I would like it to. I tried calibrating it and it still doesn't really seem to be doing its thing. But the intermolar ratio really just means take a look at the subscript. Look at how many of each element we have in the compound in question. So our intermole ratio is we're looking at how many of a given element is in a compound. It's the same thing as if we were to go around the room, if we were all together, and say how many people in the room are wearing glasses, right? You would look at and count up the number of people wearing glasses. And you would say, for our class, for every one class, we have 5 people who wear glasses. And it's the same idea here. So if we look at this first example, we want to know how many moles of sodium are in 1 mole of sodium bicarbonate. So the first thing you need to do is write out the chemical formula, because if we're going to look at the subscript, we have to know what the formula is. So remember that sodium is Na+. We get that from the periodic table. HCO3 minus, we know that from our list of polyatomic ions. So when the two come together, we get NaHCO3. So how we normally talk about this, or how we have talked about this in the past, is that for every 1 molecule of the compound, we have 1 sodium atom. How do we know that we have 1 sodium atom? Because there is no explicit subscript written. So if a subscript isn't written, remember that means that there is just 1 of that element. So in sodium bicarbonate, if we were to keep going, we would say that 1 molecule of the compound has 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. Well, we can do the same thing, but with moles instead of molecules. So note that a mole and a molecule are different. A molecule just means 1. A mole means 6.022 times 10 to the 23rd. So very different. But we can use the same idea of a ratio, where we say 1 mole of the sodium bicarbonate has 1 mole of sodium. Again, we're just looking to our subscripts in order to determine this. So what we can say is that they have a 1-to-1 mole ratio. For every 1 compound, we have 1 sodium. 1-to-1 mole ratio. So we can do the same thing down here with iron 3 nitrate. So again, first we need to figure out what the formula is. So we're told it's iron 3. So we know iron has a 3+ charge. Nitrate is NO3-. That's something that needs to be memorized from your polyatomic ions list. And then we put them together. We get FeNO3 and parentheses 3. Now we are looking specifically for oxygen. So that 3 that's outside of the parentheses gets distributed to everything inside of the parentheses. So we take 3 times 3 equals 9, and that means that for every 1 molecule of iron 3 nitrate, we have 9 oxygen atoms. And then we take this idea and scale it up to moles by saying that 1 mole of iron 3 nitrate has 9 moles of oxygen. So here, it's not a 1-to-1 ratio, it's a 1-to-9 mole ratio. 1 compound has 9 oxygens. So if instead we weren't asking, well, how many moles of oxygen are in 1 mole of iron 3 nitrate? What if instead we said how many moles of oxygen are in 3 moles of iron 3 nitrate? Well, we know that it's a 1-to-9 ratio. So if the 1 was changed to 3, then we can multiply it by 9 to get 27 as our moles of oxygen, right? 1 to 9 is the same thing as 3 to 27. They are proportional. So let's use this and tie it together with our previous slide, where we want to know how many moles of oxygen, so that's our information we're looking for, are in 3.68 times 10 to the 24th molecules of lead-2 sulfite. So here's how you'll know that you need to use the IMR, the intermole ratio. We're asking for an amount of an element that is present in a compound. Again, we're asking about an element that is present in a compound. That's how we know we need to use the IMR. So again, we need to figure out how to write lead-2 sulfite. So we're told it's lead-2, so that's Pb2+. Sulfite is one that you needed to have memorized, so SO3 2-. The 2+ and the 2- cancel out. And so I just rewrote here for ourselves what it is we're given and what we're trying to convert to. So in the black, I made some steps to kind of identify how we should approach this problem. Well, we saw in the last slide that in order to look at the intermolar ratio, we have to be in moles, right? We need a mole ratio. So step number 1 is to convert to moles. And then in order to convert from one substance to an element within that substance, we do the intermole ratio. So we can see from the compound that for every 1 mole of the lead-2 sulfite, let's see if this will let me write. Oh, not really. All right, you know that's the compound of PbSO3. We have how many oxygens? Look at the subscript. We have 3 moles of oxygen. So this is the same thing as an equivalence statement for a conversion factor. So we said step number 1 was to be in moles. So that's what we did here. And that's nothing new. We're starting with molecules, and we saw that in order to go from molecules to moles, we need Avogadro's number. So we did that a little bit earlier. And then we do step number 2, which is to change our substance. So we take this equivalence statement and we rewrote it as a conversion factor. How do we know which way to write it? Well, we're trying to get rid of lead-2 sulfite and change it into oxygen. So our molecules of lead-2 sulfite cancel out, and now we need to change our moles. So moles of the lead-2 sulfate has to be on the bottom so that our oxygen can be on the top. So now we just do the math across just like we did in chapter 1. So 3.68 times 10 to the 24th divided by Avogadro's number, 6.022 times 10 to the 23rd times 3, and we get 18.3 moles of oxygen. Now you've probably noticed that I keep writing MOL instead of MOLE for mole. And that's not an accident. It just happens to be that chemists are so lazy that MOLE, a 4-letter word, is too long. So the abbreviation for mole is MOL. So we just changed it to 3 letters. If you want to write it as MOLE, that's fine. If you want to write it as MOL, that's fine. Whichever way you choose to do it. So let's look at how we can relate masses now. We can relate masses using something called a molar mass. And the great thing about molar mass is you already know how to solve for it. Pretty much, it's just the exact same thing that we did in chapters 3 and 4. Chapter 3, we solved for something called a formula weight. In chapter 4, we solved for something called a molecular weight. And here, molar mass is done exactly the same way. It's the exact same process. The only difference is the unit. So our unit here is grams per mole. But again, we're just looking at the periodic table. And so for any given element, we can go to the periodic table. Let's say we're looking at carbon, for example. And we see carbon has a mass on the periodic table of 12.01. And so usually we would say that that's 12.01 AMU. But here we're saying that carbon has a mass of 12.01 grams for every 1 mole per 1 mole. So that's our molar mass. So this question here says, what's the molar mass of silver nitrite? Well, again, we need to find the formula or else we can't find the mass. So silver we know is a +1, nitrite, it's one that you have to have memorized. So it comes together to give us AgNO2. That means we need 1 silver, 1 nitrogen, and 2 oxygens. And go to your periodic table and see if you get the same amount as me. So silver is 107.87 plus nitrogen is 14 plus 2 times 16, and we get around 153, 154, depending on what periodic table you're using, but it should be in that general area. So we can take this idea of a molar mass and use it to convert back and forth between grams and moles. So this is exactly like what we did earlier this chapter with Avogadro's number, but this time our conversion factor is the molar mass. And something that you need to keep in mind, a common error that I see, is that students will take the value from the periodic table and write that as a mole. But that's not the case. It's always per 1 mole of the substance. So your conversion factor, again, if we were saying for carbon, you have 2 options. It could either be the 12.01 grams per 1 mole or 1 mole over the 12.01 grams. Those are your 2 options here. So just be aware that the value from the periodic table goes with the gram. So we have a question here. How many moles of carbon dioxide would be present in 10 grams of carbon dioxide? And this is going to be especially important for us because if you're in a lab setting, we can't measure out how many atoms we're dealing with. We can't measure out how many moles we're dealing with. We only have balances that measure mass. So we want to be able to convert back and forth into moles so that we can then change whatever substance it is that we're looking at. So just like anything else, we're going to start with what's given to us, which is the 10 grams of carbon dioxide. And since you know that you're given moles and grams, we know right off the top of our head that you need to use molar mass. So you would have to look up the molar mass of carbon dioxide. So again, 12 for carbon plus 16 plus 16 for oxygen, and we get 44 grams. So we need our grams to cancel out. That's why the grams goes on the bottom per 1 mole of carbon dioxide. So 10 divided by 44 gives us 0.227 moles of carbon dioxide. So let's try a few other ones. So our next one says, how many moles of potassium nitride are there if we have 100 grams of it? So, oops, I have the wrong thing written here. That's my bad. We'll work through it together then. So if we have 100 grams, that's what we're going to start with. And it's potassium nitride. So potassium is K plus, nitride is N 3 minus. So this is 100 grams of K3N. So we need to find the molar mass. So K on the periodic table is 39.098 times 3 plus our nitrogen is 14. So I get a molar mass of 131.3 3 grams per 1 mole of K3N. So we go into our calculator, and I'm getting 0.76 moles of K3N. And so there's your answer for that one. For our next problem, we're going backwards. We're starting with moles, and we want to find a mass. So same exact pattern, except this time we want to cancel out moles. So the 1 mole goes on the bottom of our conversion factor, and the molar mass goes on the top. And again, try and find the molar mass as well. Make sure that you're getting the same thing as me. So magnesium is 24.31 plus oxygen is 16, so 40.31 is what I just got from this particular periodic table. 40.325 is something I got from another periodic table. 31 and 325 are close enough that we would say that that's a match. So in this case, we multiply together and we get 228. So up here at the top, I've kind of created a little roadmap for us. We can go from grams to moles and from moles to formula units, or backwards. And so, for instance, if we're going from grams to moles, we divide by the molar mass. If we want to go from moles to formula units, we multiply by Avogadro's number. And then we can work backwards. But notice that we don't have any relationship between grams and formula units. You have to go through moles in order to get out the other side. Moles is the tunnel that you need to go through. So be aware of that. There is no direct conversion between grams and formula units. When in doubt, always convert to moles first and then move forward. So now that we understand the relationship between grams, moles, and formula units, we can start bringing this in to problems with balanced chemical equations. So this is really the nitty-gritty that chemists relate to when they hear the word stoichiometry. This idea of comparing amounts of reactant or amounts of starting material, amounts of product, or how much of your finishing amount do you have. And so how do we know when to use these steps as opposed to everything else we just learned? Well, this is all on top of what we just learned, but one way that you can know when to use it is if you are given information about one substance and you want to find a quantity of some other substance. That's when you need these 4 steps. And every stoichiometry problem can use these steps. So if you have these 4 steps memorized and down, you should be good to go, as long as you understand how to do them. So step 1 is to balance the equation. We learned that in chapter 5. Then take your given, whatever was given to you in the question, and convert it into moles. If your amount is already in moles, if it's given to you in moles, cool, ignore step 2. But if it's not in moles, you're going to need to convert it. And so that will either require Avogadro's number or the molar mass, depending on what unit you're starting with. The third step is to use the mole-to-mole ratio to go from the substance given to the substance that you want information about. And this can be done in 2 different ways. The first way is using the intermole ratio, which we looked at earlier in this chapter. The other way is to use the ratios, which are the coefficients from the balanced equation that we learned about in chapter 5. So those are the possibilities. Either the IMR, if we're going again from a compound to a piece within the compound, or a ratio if we're going from one substance to a completely new substance. And then the fourth step is to go out of moles and change the unit into whatever the question's asking for. If the question wants the answer in moles, then you're golden. You've already gotten your moles. You don't have to do any extra steps. But if the question asks for formula units or grams, then you'll need to do that last step. So steps 1 and 3 will always be used. Steps 2 and 4 depend on the question, but it always needs to go in this order. So always ask yourself through these steps, and then if you need to skip, you can. So let's try out a problem, very simplistic to start. Here we have the chemical equation for the formation of water. Remember, this little weird symbol is supposed to be an arrow. So we want to know how many moles of oxygen are required to make 5 moles of water. Now, when I have a stoichiometry problem like this, I like to pull out the information from the question and write it directly onto the balanced equation. So we're looking for oxygen. I'm going to put a question mark for oxygen then. I'm looking for it in a unit of moles. So I'm just going to write that there so that I keep track. And I'm given 5 moles of water. So this way I can see immediately what's given and what I'm trying to find. Step number 1, balance the equation. If we look at this equation, we should be able to see that it is not currently balanced. So when we're balancing, we can look at hydrogens and see that they are balanced, but our oxygens aren't. So in order for our oxygens to be balanced, we have to put a 2 in front of water, which means we'll have to put a 2 in front of hydrogen to balance out the hydrogens again. So step 1 is complete. Step 2 says to convert into moles. Well, we were already in moles, right? Our starting amount is 5 moles. So for this particular problem, we can skip step number 2 and go directly into step number 3, which is using the molar ratios that we learned about in chapter 5. So our molar ratio here is that there's 1 mole of oxygen for every 2 moles of water. And again, all I'm doing is looking at the coefficients from the balanced equation to get this 1 and 2. And I can rewrite this as a conversion factor. So I know that I want to get rid of my water, so that's going to have to go on the bottom. That leaves my moles of oxygen on the top. And then step 4 says to convert out of moles. Well, the question's asking for moles of oxygen, so we don't need to convert out of moles. So we do 5 divided by 2, 2.5 moles of oxygen gives us our final answer. In order for us to make 5 moles of water, we need 2.5 moles of oxygen. So when we meet together in class, we're going to do more intense problems that involve all of the steps. And then we're going to kick it up another notch. We're going to talk about how much product we would expect to make in a given reaction, how we can apply that in the lab, even though we're not actually meeting in the lab, and really tie it all together. Again, this is the meat and potatoes of chemistry. Very important for us to be able to measure how much product we are making, how much starting material we need in order to make a certain amount. So this chapter is going to be very important, and as you can see, it is a lot of math. So this is the kind of thing that requires a lot of practice. Take a look under the exam review resources, and you'll see some extra worksheets for you to start practicing with.